Hi, everybody. Hope you're having a good Tuesday. We're here and ready to start into section 3.7. We're doing some more derivatives. We're still doing derivatives for a while. But this section is hopefully there to just introduce you to some places where rates of change are used in different, science related um, contexts. The first one we're going to look at, biology. Um, in a biology context, you might be interested in population growth. And so you could be interested in an exponential growth model. If we were trying to model, um, a population of 15 bacteria that was doubling every hour, very busy, we could use a population growth model like this. Um, and let's go ahead and start trying to do that. You'll notice that we've got something that's e to the kt rather than, it doesn't seem like this matches with doubling right away, but we'll see how that works out. Um, let's do a quick table. If we were going to try to model out this situation, um, and we had time t and population as p of t, as an initial state, it seems like we should have 15 bacteria in our petri dish. So, boom. Then, if we are doubling every hour, I could add on an hour here. I could double here. I could add on an hour. I could double. I could add on an hour. I could double. That gives you a feeling for the rate of growth. What's cool about this is that the rate of growth is proportional to the size of the population at any given time. So, that's pretty cool. Um, if we wanted to write this as an exponential equation, maybe we would go P of t. And the most natural way to express this would probably be 15 for the amount in our initial population. You can see that that's underlined in orange here. But if I want to say doubles every hour, probably what I would do is multiply this times 2 to the t power. Um, and, that would make it so that when I plug in t equals 0, I would get 15 out because 2 to the 0 is just 1. If I have 2 to the 1 power, I would get 30. 2 squared, I would get 60, so on and so forth. This looks nice. How do we make it look like the exponential, e base over there? Well, we can use a natural log. Um, Maybe I'll come over here and go p of t. Um, let's just keep writing this. So I'll copy that. The thing about 2 is that we can rewrite it as e to the ln of 2. So we can write 2 as e to the ln of 2. Yikes. And then raise that to the t power. E to the ln of 2 is still 2 because e and the natural log are inverse functions. But when we write it this way, we can write it probably more plainly as e to the ln of 2 times t up in the exponent. And then we see that our growth constant in this case is the natural log of 2. And what's cool about this is that now we've expressed it as, a base e function. And we know from calculus that when we take the derivative of a function with a base e, we just get the same thing back. We're going to have to utilize the chain rule, so there's going to be a little bit of a hiccup here, but it works out pretty nice. Um, let's go ahead and we'll use green. Um, if we take the derivative of this, we will be starting off with the 15, and we are utilizing the chain rule here. So we are bringing out that natural log of 2. We've got e to the ln of 2t. And so, yeah, that's the chain rule. I guess I wrote the derivative of the inside part, or the derivative of the inside part first. And then, yeah, I wrote the derivative of the outside part here. So, I don't know. That's all good. And for instance, if we wanted to go over and add on, rates of change, we could think about p prime of t, yikes. And then really the major difference is that everything in our rate of change would have a factor of ln of 2 in front of it, compared to these things that we made up earlier. So, this would be 15 times the natural log of 2, 30 times the natural log of 2, so on and so forth. I think that I made this in GeoGebra, so we could take a look at it real quick. Nice. But yeah, our exponential growth model looks like this green curve. And I suppose we wouldn't want to have things in negative time, so maybe I could restrict the time on this so that it's just positive. But yeah, everything that we just calculated works out really nicely. At any given point, let's say we're stopping at hour number 1, the slope of this line is 20.77, whereas the population is about 30. So I guess maybe I didn't. There we go. That's better. Here we're exactly on 1, and that gives us an output of 30, but the slope is only 20.79. That's because when you multiply 30 times the natural log of 2, you get that 20.79 number. So it's cool. So we totally can use calculus to track the growth of a population, that kind of stuff. Yep. Great. Okay, here's one from physics. Did you know that force equals mass times acceleration is actually just a simplified version of Newton's actual second law? The actual second law says that force is equal to the rate of change of momentum, where momentum is mass times velocity. And a lot of times it works out to just be mass times acceleration because the mass isn't changing at all. But it's worth looking at actually taking this derivative because we can solve more problems, a whole new class of problems, when the mass is changing, if we consider this rate of change of momentum formulation. So let's go. All right, let's do this. If P is equal to m times v, and we take the derivative of both sides with respect to t, so maybe I'll write it like this, boom. We're going to be treating mass and velocity. So I guess, yeah, maybe I should write that down. Mass, velocity. There we go. And P is momentum. Yeah, we're going to treat all of these quantities as functions of time. And so on the left-hand side, we definitely get the change in momentum with respect to time, so dB dt. And then on the right-hand side, we have a product rule. We're treating m as a function of t and v as a function of t, just functions that we don't necessarily know what they are. And so product rule says leave one of them alone, take the derivative of the other one, and add those things together. So maybe we do the mass times the derivative of the velocity with respect to time. So I'm going to write that as dv dt. And then we're going to add that to the rate of change of mass with respect to time times velocity. Yikes. So you can see that we normally have this as, force equals mass times acceleration. But there's this other part that normally doesn't get mentioned, at least, at a beginner kind of level, because normally the rate of change of mass normally dm dt is equal to 0, and that whole term kind of just drops off. We don't pay attention to it. But if you're in a scenario like you are launching a rocket or something like that, the rate of change of mass definitely makes a difference in the rate of change of momentum, because rockets are shooting off and you're constantly losing fuel, for instance. So definitely important. And so we can see that this is available to us because we've done the product rule and we've done some kind of implicit differentiation there. So let's go down and take a look at this example. This one is not as exciting as a rocket, but we've got a freight train. This freight train is moving slowly forward at a constant velocity v under a hopper that's dropping grain at a constant rate into the train's open-top freight cars. In order to maintain its constant velocity, the train's engine must exert a force equal to the rate of change of its momentum. What is that force? So we are using kilograms for mass, meters for distance, seconds for time, newtons for force. If the train has a constant forward velocity of 1/2 meter per second and is being loaded at a rate of 300 kilograms per second, the force the engine must exert is, okay, so we're going to go back to dp dt. What we figured out earlier was dp dt is equal to mass dv dt, that's the acceleration, and then the rate of change of mass times velocity. Okay, so in this case, can we figure out what to put where? We're being loaded at a rate of 300 kilograms per second. So 300 looks like a good thing for rate of change of mass. The constant forward velocity is 1/2 meter per second. So let's go ahead and throw in 1/2 meter per second for our velocity. What's the rate of change of velocity? So what's the acceleration? Well, we're moving constant, at a constant velocity. So in this case, acceleration, that's normally factoring in there. This one's actually 0. And the mass of the train doesn't matter at all, because the acceleration is equal to 0. It's kind of weird. And yes, it would be very, challenging to make this kind of thing actually happen in real life, to be able to keep it at a constant speed by continually applying a certain amount of force. Yeah. But the mass of the train doesn't really matter. But what that tells us is that the overall force being applied should be, 300 divided by 2. It should be 150. That would be, if we were going to really try to do a good job with the units here, that would be kilograms per second. And then we will be multiplying that times meters per second. And a kilogram times a meter divided by second, I think that's newtons per second. I believe. I could be wrong. I didn't actually look it up recently, but um, yeah, we should be applying force so that as this is loaded down with mass, we can continue to maintain the same velocity. Kind of interesting. Chemistry. I'm sure that you are all somewhat familiar with chemistry. Um, a chemical reaction might take in a couple of reactant substances and then produce a product in the end. Um, and the idea is that we can capture something called the reaction rate. Um, in my mind, this chemistry one is not super exciting. Perhaps for those of you who are in chemistry, maybe it is exciting. Um, I like chemistry, but this specific problem formulation is not extremely difficult in my mind. It's more about just ratios. Um, the idea being here, if we've got nitrogen gas and we are adding hydrogen gas to make ammonia, we just need both sides of this uh, chemical reaction to be balanced. Since we have two molecules of nitrogen in gas form, diatomic, just floating around. Since we've got two molecules of nitrogen, we want to make sure that we have two molecules of nitrogen over here. And since we've got, six, hydrogen atoms over here, we want to have six total hydrogen atoms over here. And the idea to make that equation work out right, it's like a recipe. Like you've got 1 part nitrogen to 3 parts hydrogen, ends up making 2 batches of ammonia. Um, and so in my mind, I left the solution here in terms of reaction rates. Like we could delve into the details of this if you're really interested, but what ends up happening is that we're always in this kind of a ratio of 1 part nitrogen to 3 parts hydrogen into 2 parts ammonia. And the reaction rate, might is, you know, it doesn't, I don't know, like it's just a constant kind of thing. We can scale it up or scale it down, but it doesn't really change overall. Um, so the idea being is if, you know, we are measuring the amount of ammonia at 1.2 moles per liter hour, then we're changing the concentration of the substance by that many moles per liter per hour. And that just means that the reactants are changing in kind. So since this was, 2 batches of ammonia, um, we're losing 3 batches worth of hydrogen and we're losing 1 batch worth of nitrogen. And, we're still in the same ratio. This is a ratio of 1 to 3 to 2 again. And it's not like super exciting. Maybe something like this, if we wanted to visualize it mathematically, we could like put it in a vector and we could talk about it in a multivariable context where we're able to scale that vector by the reaction rate. But yeah, I don't know. It's all cool. Chemistry's chemistry's fun, but this problem was like 4 out of 10. It's all right. Yeah. Um, okay, last one from this section is business or economics. Here we are trying to represent the number of workers in a given industry at time t. We're going to use WT for that. And then we've got P of t represents the average productivity. And what we're going to try to compute is the gross productivity. And that is given by multiplying the number of workers times the average productivity across all the workers. That would give us like the total productivity of everybody. Suppose that it's known that at a specific time t, the labor force is decreasing at a certain rate um, relative to the size of the labor force of 1%. This translates into the statement that the rate of change of the workforce is, negative 0.01 times the current amount of workforce. And this is the kind of data that's more commonly cited than absolute data, especially when you're working at like an entire country's, scale of workforce or something like that. I guess here we're working in an industry. Um, Suppose that at the time it's also known that the average relative productivity is increasing at a rate of 3%. Great. That second fact would tell us that the rate of change is proportional to the amount at that certain time. So yeah, that's good. We could use those two pieces of information to determine the relative rate of change of gross productivity. And so again, we would be in a scenario where to calculate this gross productivity number, we are multiplying two functions of t. So let's go and we'll copy this down. So g of t is equal to w of t times p of t. And to get g prime of t, we could use a product rule. So we could go w prime of t times p of t, whoops, and then plus w of t times p prime of t, just the other way around. And then we can start filling stuff in, making substitutions that make sense. Yeah, since we already understand that the labor force is decreasing, we could go and substitute in negative 0.01 WT in for W prime of t, and that would be multiplied by P of t. And then W of t can just chill, and we'll multiply it times P prime of t, which would be 0.03 P of t. And so, yeah, in one sense, we're going to be subtracting off 100th of this product. That's the part that we're losing because the labor force is shrinking. And then we're also going to be adding on 0.03 due to the gains in productivity. And so since those are now like terms, we could multiply them together. That's a nice thing about having these relative changes to our population. 0.02 WT P of t, and since WT P of t is the gross, I'll just write it to the side. This is like 0.02 gross productivity. So again, we're dealing with some very basic differential equations here. And we end up getting a result using the product rule that says overall, yeah, we're gaining in productivity. That's cool. This again is like an introductory thing, but calculus is used in business and economics all the time. I mean, a lot of stuff at this point is probably encoded into things like Excel and all that good stuff. But underlying this, there are principles about rates of change underneath it. Cool. So that was, I don't know, that was 3.7. that's just to give you a flavor of some different areas where this calculus can be applied. There are many more. Um, and now we get to get into good stuff. Let's go to section 3.8 and work on some related rates. Um, Here we are going to be changing things with respect to time. And we're going to be, yeah, I mean, I guess relating different rates together. We're going to be interested in understanding how one thing changing affects another thing changing. For this first one, we've got a cylindrical water tank being emptied at a rate of 100 liters per minute. How quickly does the height of the water level fall if the radius of the tank is 1 meter? How does the answer change if the radius is 10 meters? Okay, we'll leave that for later. Let's focus in on the 1 meter first. Okay, so what's the idea here? Whenever we're starting off with a related rates problem, we want to create an equation that relates the important quantities especially the quantities that might change. Okay, so actually, let's make sure that I'm not doing this too bad. I'm gonna bring this up. Lasso that, oh, nope, just kidding. Forgot it wasn't gonna give me a lasso. Let's bring this up and we'll write it over here. But that's, first thing is create an equation that relates the important quantities. In this case, it looks like we've got a cylinder and we're interested in finding how fast the height of water in the cylinder is changing. And we have information about, here, let's go ahead and just, you know, real briefly label these. Um, this is a rate of change of volume. Okay. Um, this is, height of a cylinder. So that's, that's a length. Um, the radius is another important one. That's also a length. And so if we wanted to, and I guess here we've got cylinder is another thing here. If we want to coordinate volume, height, radius of a cylinder, we could use the formula for the volume of the cylinder. So this one, let's go V equals pi r squared for the area of the base of the cylinder. And then to get the volume, we multiply times the height that's perpendicular to the base. So pi r squared times height gives us the formula for the volume of a cylinder. And that's a cool equation that relates the relevant quantities. Notice, though, that we don't have any calculus type stuff yet. We don't have any rates of change. So dH dt, totally still a question mark. dV dt, we've got a number for it, but it's not in our equation anywhere. So second part of this is to take derivative with respect to time. So it's good that we've started here with a very general equation, and we've got three different variables. If any of these variables we knew were just going to stay constant, we could technically plug in numbers for them at this point. But since the volume could be changing in this scenario, the radius, I guess, the radius is not necessarily going to change. Um, in this first example, the radius is 1 meter. In the second one, the radius is 10 meters. So we would have a choice to make here. If we know that we're going to do this problem a couple of times and we want to be able to change the radius, maybe we leave r as it is before taking the derivative. But if we wanted this to be more flexible, it doesn't hurt to leave r as a variable and, you know, still just take the derivative with respect to time of everything, because then we'll be able to change that if we want to in the end. So on this one, especially since we're going to do it twice, let's just leave r alone. And h is definitely going to change. The height of the water is definitely going to change. So we definitely want to leave that one. R is a little bit of a gray area. I think I'm going to elect to just leave r in there for now, especially because if we do, we're going to be able to do a product rule, which is fun. And if I made r a constant, then we wouldn't have to do a product rule. And like, what fun is that? Anyways, let's go ahead and take the derivative with respect to t of everything. We get dv dt over here. I'm just going to leave pi out on the front here. And let's just focus on our product rule being r squared and h, and we'll just, focus in on that. So for the first one, I don't know, let's take the derivative of the first one. So if we take the derivative of r squared with respect to t, that turns into 2r times dr dt according to the chain rule. R is some function of t. That's our little function. So we've got 2 times something times the derivative of the inside, which is dr dt. And then we're going to add that to, leaving the first part alone, r squared, and then taking the derivative of h with respect to t. Wait a second. Yeah. What did I do? Oh my goodness. Y'all, I forgot to write h over here. My bad. This is the derivative of the first part, and then times the second one, the second function. My bad. And then r squared times the derivative of the second function, which is in this case is just going to be dh dt. Oh my goodness. All right, so I'm going to erase that little thing. Get out of here. That looks like a good product rule. And in the case where the radius isn't changing, notice that that first term is just going to go to 0, and we won't have much to do with it. So I guess in this case, that is going to kind of drop out. But by leaving r as a variable in this, it will enable us to, change that quantity. Maybe I should have just left that as a constant. Anyways, yeah, let's see if we can plug things into the right spot. You know, plug in numbers. So dVdt, that is losing 100 liters per minute. Do we want to change this? Here we've got radius of tank is 1 meter, and they gave us this conversion factor between 1 liter is a 1/1000th cubic meters. I suppose we should just work with that. All right. So let's convert everything into cubic meters. If this is losing 100 liters, 1,000 liters would be losing 1 cubic centimeter. This works out to be, losing 100 liters, over 1,000 liters. Here, we'll do a conversion factor like we would do in chemistry. I gave you a Lane chemistry example earlier. If we're working with 100 liters per minute. And we multiply it by a conversion factor where there are 1,000 liters in a cubic meter. Boom. 1,000 liters in a cubic meter. The result that we get, I can go one step below this, is negative 0.1 cubic meter per minute. So we're losing 1/10 of a cubic meter per minute if we're going in cubic meters. All right, then we've got pi, then we've got 2, then we've got the radius in this first scenario is 1. The RDT, well, I guess sadly that's going to be 0. If we had some kind of, if we had some kind of cylinder that was changing in radius, and the first thing that made me go, ooh, I thought of like a blood vessel. If this was some kind of blood vessel that was pumping blood and the radius was changing, then this term could be useful. But as it is, the radius is not changing, so this part's pretty garbage. The height being h is fine, but I mean, it's not really going to affect anything, so we don't have a number for h right now. But thankfully we've got a number for r. Yeah, we've got 1 squared for that part, and dh dt is the thing that we're solving for. So I will leave that as dh dt. So simplifying this, we've got negative 0.1 is equal to pi times dh dt. So maybe I'll just, not even bother with the brackets. And so dh dt is equal to negative 1/10 divided by pi. What a wonderful number. This is a math class. Cool. And how would this number change if it was a radius of 10? All right, let's go. Radius of 10. We would go, well, the main thing that's going to change is that 1's going to change to a 10. So we would have negative 0.1 equals pi times, we're still going to have 0 for that first term, but then we would have 10 squared times dh dt. Goodness. And then that would mean so that we've got 100 pi over here. And so we divide by 100 pi, and we'd end up getting, well, if we're working with decimals, why not just throw, oh, geez, we don't need that many zeros. I guess divide by pi. Lovely. And yeah, do I have exact numbers for those? No. Do I have approximate numbers for the? I mean, I guess those are exact numbers. I don't have approximate numbers for those. You divide by 3.14, and those are numbers. The change in height. But that's the general feeling for these problems is that you want to create an equation, and sometimes this takes a little bit of creativity, but you create an equation that relates the relevant quantities. You take the derivative of everything with respect to t, and then you plug in the numbers. Our book has 5 steps instead of 3. Sure. And this one, it's nice to identify what's known and what needs to be found. You want to find, determine your overall goal. You want to find the rate of change of one particular variable with respect to time. There's drawing a diagram can often help. Write an equation that expresses the relationship. So that's kind of step 1 in mind. I mean, you definitely want to take the time to think through things first, and then you make your equation. Then you use the chain rule and differentiate everything with respect to t. And then you solve for the rate of change by plugging stuff in. Let's see if we can do maybe 2 more of these. If we do 2 more, we're going to be in a good spot for for Wednesday. Okay, example number two. We've got a hot air balloon rising straight up. Um, it is being tracked by a film crew stationed 200 meters away on level ground from its takeoff point. At the moment when the balloon is 150 meters up, it's rising at a rate of 50 meters per minute. How fast is the camera angle increasing at that moment? So I guess I've kind of cheated and I've gotten myself this nice diagram already. And I don't know, it doesn't make sense to get rid of it right now. But this is the kind of thing that we would want to get used to drawing. And so hopefully, if we look at the problem, we could kind of think about how to draw this thing. I think it's nicer to use this than something that I would just draw hand for this example. Um, cool. So let's identify what's changing, what's important, what we're trying to find in the end. All right, we've got the first number that we come up with. I guess a hot air balloon is rising straight up. So that's something that is changing. That's a change in length or speed. So that's a change thing. 200 meters away, this is a length for the leg of a right triangle. At the moment when the water is 100 or when the balloon is 150 meters up, so this again is another length of a right triangle, and it's rising up at a rate of 50 meters per minute. So that 50 meters per minute is the rate of change that I underlined earlier. This is change in length or change in height. I'm not using length and height to specify, I don't know, different things like you would think area of a rectangle is length times height, um, or length times width or whatever. These are the same things. All I'm trying to say is that we would measure these with a ruler. Um, their distances. So that's cool. Um, the last question is how fast is the camera angle increasing at that moment? So here we are looking at uh, rate of change in angle. Oh, so do we know any equations that relate lengths in a right triangle? I guess maybe just writing this out once. We want an equation that relates lengths of a right triangle to an angle measure. Triangle to angle measure. Well, the best functions I know for that are trig functions. And in particular, if we were taking the time to sketch this out nicely, which has kind of already been done in the picture, we could say, yeah, we've got this distance of 200 meters from the camera crew to where the balloon took off. So that's a nice side length. We've also got this height, and we could call that y because that's a change in vertical distance. We could label the change in that variable as dy dt. Um, we could label this angle where the camera crew is standing as theta, and then the rate of change of that angle as d theta dt. And once we've made those labels, we could see that we have the adjacent leg of a right triangle, we have the opposite leg of a right triangle, and we've got an angle. And so what kind of, relationship is there between an opposite and adjacent? Let's use a tangent. So, the tangent of theta is equal to the opposite over the adjacent. In this case, the opposite leg is y, and the adjacent leg is 200 meters. I'm going to leave it like that. Right now, notice we don't have any rates of change yet. We'll get that when we take the derivative. But this should just be an equation that stands on its own and relates important quantities together. So the tangent of that angle theta is equal to opposite over adjacent. That's looking good as a start. Then we take the derivative with respect to everything. So everything with respect to time. So we're going to go, I'll go ahead and write it out just so that we're on the same page. And, notice here that we are completely happy to have different letters in our equation right now. We've got a theta, we've got a y, we've got a t. It's totally cool because we're taking the derivative here with respect to t, and implicitly we are treating the angle and the height y as functions of time. And so when we take the derivative of the left-hand side, we're going to get, okay, what's the derivative of the outside function? The derivative of tangent is secant squared. So we've got secant squared theta. We're leaving the inside the same. And then by the chain rule, we are multiplying by the derivative of the inside. So that's d theta dt. So that is the result of the chain rule. We take the derivative of tangent, which is the big function. We get secant squared theta. And then we multiply by the derivative of the inside, which is d theta dt. Then, on the right-hand side, we do the same thing. The derivative of y with respect to t, I mean, that's going to be kind of boring. This is just a nice linear function. That'll be dy dt. And we've still got that factor of 1 over 200 coming along. So I don't know. I'll write that there too. Maybe we'll keep that. I don't know, parentheses? Sure. But yeah, that's what it looks like to take the derivative of everything with respect to t. We had a chain rule on the left-hand side because we had theta inside another function. But so far, so good. We took the derivative. Now, if we've done this correctly, we should be able to plug in numbers. Plug in numbers. What do we got? We've got a 200 and a 150, and we've got a 50 meters per minute. Okay. So the 50 meters per minute, that goes into the change of height. And I guess that means we're going to be measuring things in meters per minute now. And that, could be useful. Secant squared theta. This is not a quantity that's necessarily like changing, so we should just be able to calculate this based on the triangle. So if we scoot over here and we say, okay, what is the secant of theta of this triangle? Well, the secant is 1 over the cosine. So this is not adjacent over hypotenuse. It is hypotenuse over adjacent leg, where in this case, the hypotenuse is going to be not one, okay, 150 is over here. And then we've got 200 on the bottom side. This is going to be a 3, 4, 5 right triangle where the hypotenuse is going to be 250 meters. You can check that with the Pythagorean theorem. You could find it with the Pythagorean theorem. But I'm just going to say that's a 3, 4, 5 right triangle in that ratio. And so we know that the hypotenuse is 250. So we've got 250 over the adjacent leg of 200. This is a fraction that can be reduced to 5/4. So I'm just going to write 5/4 squared there for secant theta squared. And then d theta dt, I guess that is the thing that we're solving for. So we just let that chill and reduce the rest of this. So 50 over 200, that's 1/4. All right, so d theta dt is equal to 1/4 times 4/5 squared. Just gonna do that. That gives us 4 over 25, and we were working with meters per minute in our length velocity kind of milieu. We are using radians per minute here. So 4/25 radians per minute. I know that I'm used to measuring radians in terms of pi and that kind of stuff, but 4/25 radians is per minute is how fast the angle is changing on that camera lens. Okay. We're doing well, especially if you guys have been watching me at a decently fast speed. We're gonna have plenty of time for example 3. If it looks like we've got only 5 minutes of class left, maybe we'll need to pause and we'll need to do this tomorrow, but this should be fine. Example 3. Susan's in her car, leading a group of other drivers to a restaurant. She's just completed a right turn at an intersection and is accelerating away. So she's in the blue car. At the moment, she is 40 feet away from the intersection, heading north at 25 feet per second. A second car in the convoy is still 40 feet away from the intersection and is approaching at 15 feet per second. How fast is the as the crow flies distance between Susan and the second car increasing at that particular moment? So we're gonna do this the short version. No, we're gonna do a good job. We're looking for the rate of change of this hypotenuse eventually. And so in this scenario, we've got a side length, we've got a side length, we're changing the side length, we're changing this side length, and the hypotenuse is changing as a result. And so what kind of equation could relate the side lengths of a triangle to its hypotenuse? Well, Pythagorean theorem probably. That would work really well. So in this case, this leg has been labeled as x. And, if we're changing horizontal distance, x makes a lot of sense. So x squared plus y squared equals h squared is a good Pythagorean theorem that should relate all of these distances. So if we wanted to relate the distances right now, we would have 40 squared plus 40 squared equals 40 radical 2 squared. So this looks good. This looks promising. Second step would be take the derivative of everything with respect to t. So we get 2x dx dt according to the chain rule. We get 2y dy dt, again according to the chain rule. And then we get 2h dh dt according to the chain rule. And then we have this wonderful equation where we can start plugging in numbers. At this moment in time, we've already got this nicely labeled. We are 40 units away from the intersection. And if we wanted to be really persnickety, we could probably, figure out whether we want to make this positive 40 or negative 40. In this case, in regards to this intersection, it kind of looks like we are, operating in the first quadrant of stuff. We're 40 units to the right, we're 40 units up from this corner of the intersection. So I'm going to label both of those as positive numbers. However, when we look at the rates of change, since this one is increasing and yeah, making this length bigger, we're going to give that a positive. Since this one's getting smaller, we're going to give that a negative. That makes sense, hopefully. So let's go ahead and fill in the numbers. X here is 40, dx dt is shrinking. That side of the triangle shrinking. So we're going to do negative 15 feet per second as a number that we throw in there. Here for y, that again is 40, and dy dt is happening up here. We are increasing at 25 feet per second. We do know that the hypotenuse of this is 40 times the square root of 2. This is an isosceles right triangle. 40 square root of 2. If you didn't know that this is an isosceles right triangle and that you can find this by using that ratio, you totally could use the Pythagorean theorem to use 40 and h to solve for h. But then we're going to leave dh dt there because that's the thing that we're trying to solve for. And so we should just be able to work this out and see what happens. You know, if we're adding all this stuff together, it looks like we're going to add 10 copies of 80. So it looks like this should shake out to be 800 on this side. And over here, we should have 80 radical 2 dh dt. Go ahead and check me on that. I guess I could be wrong. But yeah, then we should be able to divide both sides by 80 square root of 2. And I guess that would be 10 over square root of 2 equals dh dt. If it bothers you to have a radical in the bottom, you could multiply the top and the bottom by the square root of 2, and you could get 5 square roots of 2. But, you know, that's the same thing. And so that is the rate of change of the hypotenuse. And this worked out to be a positive number, so the hypotenuse is increasing. But yeah, that tells us how fast the hypotenuse of that is changing as both of those side lengths are changing. So, super cool. We'll look forward to a couple more related rates problems on Wednesday, and we'll talk about linearization and differentials. It's going to be a good time. Looking forward to seeing you then. Have a great day.